Next will be our exciting and interesting lightning talk session. We have 7 talks, and so we have about 5 to 6 minutes for each speaker. And myself, I'm Yung Guan, a professor at Iowa State University. I work with my colleague, Professor Mai Zheng and Saras Babu, to co-lead the software working group for ARA project. And so our first speaker, our first talk will be given by Professor Ashwin Ashok from Georgia State University. I will keep my introduction very brief because of the short time for the presentations. Yes, please come. And you can find your slides if you want to see the slides. Yeah.
I think right after lunch, last thing is show slides. Anyway, thank you for the opportunity. I'm audible, right? Thanks for the introduction and this opportunity. I'm Ashwin Ashok. I'm an associate professor in Georgia State University, and I work primarily in the area of mobile computing, robotics, wireless communication, so very much belong to this community. First of all, kudos to the ARA team for all the launches, wonderful things, and things that they're going to show more. And great hackathon with the students. For what they showed just in a few hours is just mind-blowing. So just to relate to some of the things that ARA is doing and why ARA is, could be helpful for some of the things that I'm doing, I just want to give some background on a couple of projects that we are doing back in Georgia State, where we're particularly focusing on not on agriculture, but some of the themes that were talked about. One is soil. We're very interested in understanding how radon gas particularly diffuses through the soil, its penetration through the soil, its transportation. Radon gets generated from the disintegration of uranium, which is already there in the bedrock. It comes from underground. And the more volcanic region it is, then, or felsic rocks as we call, these regions have high potential for uranium and hence radon. Radon comes from it's a gas, it's inert, does not react with anything, and it just percolates through different fissures of your soil. But there has been very less understanding about how radon really transports under the soil, and it gets into your home, and then some of you may have done these radon mitigation systems or tested for radon. And why is radon important? Radon is the second biggest cause of lung cancer after smoking, and all over the world, not just US. And there are a lot of radon initiatives trying to study that, and we are trying to understand what really happens at the source, so more so. I'll come to the question of what is the problem there, but I also want to get to the other dimension of a problem that we had, other dimension of a project that we are looking at, where we are trying to deploy some nanosatellites, or CubeSats as we call, and I think Ranveer mentioned a bit about what they're doing. We are interested to study the cosmic rays, particularly that have been generated right from Big Bang, which are always there. And the theory is that when these cosmic rays actually penetrate through our Earth's atmosphere into the layers of the crust, they get modulated by the layers of the atmosphere. And they get modulated because of the geomagnetic changes in the atmosphere. Geomagnetic changes are caused by different space weather changes. And majority of our space weather changes that we are typically interested that cause the geomagnetic disturbances is solar weather. So in a way, we are trying to understand solar weather through these nanosatellites, just trying to understand the cosmic ray flux right above in our low Earth orbits, medium Earth orbits as satellites, and what happens right after they penetrate through the atmosphere on the surface. So trying to see this difference of flux, we are trying to get a proxy for solar weather. And we just, we had a hackathon team talk about weather, and they talk about humidity, which is a big parameter, both for soil and this. But as we know, whenever we talk about communication systems, geomagnetic storms, solar weather is a big deal. You get, and we had some. And just to let you know, as you know, solar cycles go over an 11-year period. And the bad news is that we are in the peak of that solar cycle, and next year is going to be the high. So it's going to be much more hotter, so just get ready for it. So in that interest, We are I'm very interested to see how the multimodality aspect of Era deployments in terms of the communication and networking across can be useful for really augmenting some of the experiments that we're doing. And it's not a one person's job, and we can see the kind of deployments that are there, especially the fact that you have a farm to cloud kind of, or literally almost soil to cloud kind of connectivity here. We are interested to see how we can collaborate with this team and try to really understand, try to solve these problems which require more than scratching the surface and also going high up in the air. I'd really like to thank you for the opportunity, and I don't think we are taking questions. I'll invite the next speaker. Thank you.
Thank you. So next speaker will be Marty Candice from San Diego State, San Diego Supercomputer Center.
Does this work? How do we? There we go. Okay, great, thank you. So thank you for the opportunity to give a quick little talk and give you a flavor of like what I'm working on as part of the Icicle project, which is one of these NSF AI institutes that's been funded by the Office of Advanced Cyber Infrastructure. So this is sort of how someone from high performance computing gets involved in wireless communication and digital agriculture sort of applications. So just a little bit about Icicle. I've basically given a quick summary. It's funded by the Office of Advanced Cyber Infrastructure. The idea is to understand sort of the challenges of building the infrastructure that's required to deploy AI solutions into the real world, essentially. This is why it's called computational learning in the environment. And the project is, a very large project with, I think, 14 different institutions, about 100 people or more involved. So there's many different projects that are going on within Icicle. And my part is very small, working with people like Chris Stewart and Hong Wei here at Iowa State on some of the agricultural applications that we're thinking about. But it's a use case driven institute. So we have sort of three major areas of focus: the agriculture space, obviously here. There's groups working on animal ecology applications and food systems. And so each one of the teams involved in the Institute is working on specific applications of what cyber infrastructure is needed to be created, deployed, or modified to tackle some of the problems that the research scientists in these spaces want to tackle in the future with artificial intelligence. Myself, I'm a high performance computing person by nature, and so I've been looking at more of the scalable data management problem that you see in all of these AI applications, right? If you want to do AI, you need lots of data, and moving that data around, putting it on high performance computing systems to train models, getting the data from the field, it's a complicated problem. So what I've mostly been focused on is looking at the different types of data infrastructure that's already deployed by many other NSF funded projects around the country. This is just a quick experiment that I did last year, comparing dumping essentially millions of files of JPEGs onto our local file systems on our supercomputer at the San Diego Supercomputer Center, versus testing this distributed file system that's got this sort of caching network around the country that allows you to distribute large data sets, to any sort of high performance computing center across the country. And as the caching layer sort of builds up that local copy of the data, you sort of get local performance with this sort of application here that we were working on. But as I think many people here know, these problems of the types of sensors and the data that could be collected from the field, it's a lot of data if you really wanted to push the limits. And the thinking about the problems that of getting that data back from the field to the data center for this sort of, AI model retraining type of workflows that you'll see in a lot of these applications is sort of a bit mind-boggling of how it's actually going to happen. So this is what, test beds like Ara will be really great at exploring, of how we actually do the plumbing and what software applications that need to sort of manage that data flow from the edge to the data center or to the cloud. So one thing that I've been thinking about in this space is sort of that edge collection problem. Like, how do we take some of the tools that we already have available, used in different applications, and apply it to this edge data collection problem? How do we aggregate the data back to the data center, essentially? And so this is one piece of software that's actually used as sort of a content delivery network for delivering software and data from, data sources to edge devices. But, in theory, we could turn this sort of content delivery network software around from making the edge devices the sources and using it as an aggregation service to bring the data back to the data center. Another project that I've been working on a little bit more recently is using this sort of distributed scheduling software that I've used before in the past called HT Condor, which has a built-in data transfer layer into the system as well. And it's a very flexible distributed scheduler where you can actually easily turn different nodes and devices in this cluster into different flavors of nodes. So you can actually have, in some cases, like the compute node on the edge and a submission node on the edge, be able to not only run workloads at the edge, but then submit workloads back from the edge to the data center. And so this is one of the demos that I'm kind of still working on to try to make it a little bit more fancy later today, but I've sort of initially deployed one of these sort of test bed clusters onto Ara recently, and sort of being able to move around these computational workloads and moving data between UEs and the data center or to the edge computing at the farm is kind of what I've been working on recently with Ara. So hopefully it gives you a little flavor of what I've been up to, and I just want to thank all of my collaborators at the Icicle Institute.
Thank you, Marty. Yeah. So our next talk will be given by Professor Chang Liu from Nebraska Lincoln.
Hello, everyone. This is Chang Liu, Assistant Professor at Nebraska Lincoln. Today, I'll just try to briefly talk about what we are working on for the private network for the campus as well as the agriculture scenarios. This is one of our projects from the NSF campus cyber infrastructure program. So the backgrounds briefly, like we know that we lack of the infrastructures. Well, Iowa, Nebraska, the whole Midwest. In terms of our, because that was the campus cyber infrastructures, we see they obstruct a lot of research projects on campus because we are in, same with Iowa, we do a lot of agricultures, actually many of them. So the question was, why not use the public mobile networks? We are in the very good, the great branch, we have limited coverage of the rural and agriculture scenarios. We have a remote research farms out of our urban areas. So they basically have very limited public wireless network there. And some of those applications require some performance, not just simply satisfied by the public mobile networks. So we proposed in this work to do the private network to tailor the network to meet the requirement of different projects. So we call it a host connect. This is the first 5G network in Nebraska. So we have some features in terms of cost efficiency, management automations, and performance assurance. Well, we basically have two tracks. One is the commercial of the track. Basic idea is we get some commercial base stations, and then core networks with 24/7 availabilities and reliabilities, so that they can be easily to support more than hundreds of users on campus, including the research farms. And the software-defined radio tracks, which is based on the SDRs as AIA platform is doing right now. So we're based on the SDR boards to build end-to-end 5G, live 5G networks on campus. We also have some mobile site, quite interesting. So because we have some project that has to go very, very far without any, no connectivity at all, any kind of connectivity. So we designed a mobile site with the base stations, with the converters, and with the starting to connect as the backhauls. It's still ongoing, by the way. There's some architectures we currently have. Well, we haven't built all fully yet, but that's what we are doing for this whole project. So some features, we enabled network programming capabilities and virtualizations. We achieved predictable end-to-end performance because myself doing quite a lot of regarding network management and network slicing, so that we can effectively automate these slicing parameters to tailor this slice to different kind of users and applications. Because we have limited backhauls in different scenarios, in research farm, in middle of nowhere, middle of Nebraska, very middle of Nebraska, and then we have convergent RAN edge and core architectures, so that we can do and process the data at the edge before it sends to backhaul to the core. So we support quite a lot of scientific projects on campus, agricultures, which is one of the big portion of it, with the agriculture sensors, UAV swarms, livestock. There's some pictures we have. We also have some more performance critical applications like connected vehicles, robotics, safeties in the construction zone, as well as we have some environmental monitoring in the middle of Nebraska, there 100 miles away from Lincoln, Nebraska, and Omaha. So next step, briefly, we are trying to build digital network twins of the host connect. So we consider host connect as the kind of we call the real world networks. It's actually operating and running, supporting, getting data. Is a live network, and we try to build a digital network twin. But digital network twin is to try to do some to support the emerging AI and machine learning training and testing. If we want to control the network, we want to predict some metrics for the live networks. So we don't want to actually control it for the actual infrastructure network that will have safety issues. We I say safety is like, crash the network, something like that. So some application for that, we are welcome some the community to say I have some inputs, insights, and comments. So co-design next generation of digital network on behalf of there is a backend or live networks operating there. I think thanks. Hopefully I get the time. So again, I'm a Chang Liu, assistant professor in Nebraska.
Yeah, thank you, Tim.
All right, thank you.
Our next speaker will be from Canada, because he's the only remote speaker, so we switched the order a little bit, so we're going to ask Dr. Eudoro Baena to talk first, and then Professor Jianping will talk at the last in the session. So, okay. Yeah, you're the next. Yep.
And this one. It has some animation, like it would work. Let's see. Okay, so good afternoon. My name is Eduardo Baena. I work at the Institute for the Wireless Internet of Things at Northeastern University in Boston. And first of all, I want to congratulate you for being alive. Maybe you are surprised and why I say so. So, for many reasons, but the one that brings me here is because if you already don't know it, we are witnessing a new era of human space exploration. So a couple of questions that I want to start with is, why are you so excited about this space stuff, space race? What is so special about it? So first of all, I am a cellular guy, let's say. I come from the cellular world. We are so proud to have one of the most used wireless access in the world. But the problem is, like, there is this digital divide that we have been discussing here with this environment. And unfortunately, the cellular phones, the cellular coverage is only the 10% of the Earth. So we still are far off covering, the whole territory. So, and the second reason is, like, the space is sexy, right? So why the space is so sexy? Well, I have found like three main reasons. First of all, it's hard. It's like extreme conditions, and there are like many students try to launch CubeSats, nanosats, and it's really difficult because the conditions of the space are really extreme. But also this is an advantage because, for example, for some agricultural applications, you can get to know like certain conditions makes you wiser, let's say, in your field. So there is like space agriculture, which is bringing back to Earth a lot of knowledge in this field. The second feature of the space, why space is so sexy, is because it's scarce. And this, for engineers, is a very challenging problem. So, when you launch something to space, you need to really think about it. What are you launching and how are you going to use it? Because, energy is scarce, hardware resources are scarce. So, yeah, there's a problem. And it's crazy. I mean, it's highly unpredictable. I mean, in the wireless world, there is a lot of interference. There is a lot of things that we don't know that can happen. So, if we like problems, if we are engineers at heart, we love problems, the space is the perfect place for us. So, and then, when I say this to my colleagues, they say, hey, but is not all the job already done? How's the name of this guy? I don't remember, like Elon something. So, he already solved all the problems of humanity. So why are you caring about this, right? So, I mean, I will have like few questions to make to Mr. Musk. So first of all, unfortunately, he's not here to answer them, but let's try. So first of all, what happens, with the Starlink direct-to-cell communication? Can you use your normal cell phone to communicate with Starlink, or you need this big dish, connected to some, energy from nowhere? The second question is like, what is the interoperability with actual cellular networks, with 5G networks? Can you move your dish to connect to 5G I don't know. Probably he will be handling these questions like pretty straightforward, but fortunately he's not here. So how many simultaneous users can support the actual Starlink constellation? I mean, because compared to the cellular, if you are alone in the middle of Alaska, maybe if you are just, using the satellite for yourself, you will have a good throughput. But, if we are considering agricultural, digital agricultural use cases and these kind of things, I'm not sure. So what about performance during mobility? You want to move like you do in the cellular world? Let's see what happens. What about QoS, QoE? Can you support that, Mr. Musk? And then customize. What about customizing your connection with the Starlink? Is there? And are your constellations really resilient to support like really extreme use cases? Probably he would be, answering all these questions like quite straightforward. So here is like the approach that I'm, let's say, leading. We are proposing to use the ORAN architecture in space for 6G. So what we are talking about? So let's picture where we should arrive, okay? So if we see the regenerative satellite as a programmable radio computing facility, the ORAN architecture is the best choice for integrating the cellular with the satellite networks. So this is the ground deployment. So this is like computing facility on Earth, like the cloud. And this is, let's say, if you consider it like on the air deployment, then it's like you have some edge computing and radio programmable resources that are, let's say, on the sky. So some of the challenges, for example, just to mention a few, interference. So you are transmitting from the satellite, but what happens, if we use the same bands, okay? There will be some interference, like serious interference problems. Also, what happens with mobility? I mean, that LEO satellites are moving quite fast. Maybe the coverage that it lasts for, I don't know, 5 minutes, 10 minutes. How can we handle this? So this is like the perfect match for ORAN architecture. Why? Because it's softwareized. So that means, hey, I want to upgrade the new 3GPP version, so you can do it, let's say, via software. It's virtualized, so we can use it very efficiently on demand. It's open into innovation, and also disaggregated, so gives you more resilience and more possibilities to play around with the ORAN standards. And also it's secure, because if you follow the 3GPP standards, it can be a chance to secure the satellite networks. And just a quick vision for the future. If we keep dreaming, I mean, if we are serious about going to the moon and to Mars, we need wireless there, You need to keep watching your Netflix, even if you are living in the moon. So, yeah, basically, I am leading an initiative called LEORAN to extend our Colosseum infrastructure back in Northeastern, to develop this kind of LEO technology with ORAN. And if you are interested, just let me know. Thank you.
Thank you. So our next talk will be Jie Wang, a PhD student from Washington University, St. Louis.
Thank you. That's a great talk. I forgot to put my LinkedIn profile here, so if you're interested in my talk, feel free to talk to me or just ask me questions. So it's JW here, this one. right, thanks. Thanks also, Professor Guan, for the introduction. So I'll just stick to the 5-minute limit, so I'll just get started. So the title here is to explore new potential of wireless spectrum through learning and systems approach. So it's a long title, and we have talked about so many wireless applications like satellite communication and O-RAN and all other ones. So let's talk about, all down to the bottom, let's talk about wireless spectrum. So to start with, why do we need to explore new potential? And the answer is simple. We always need more spectrum for higher data rates. For example, for live streaming, for high quality video recording, or even for like cloud gaming or other uses. But the fact is, the wireless spectrum resource is limited. So what can we do with it? So the general framework that has been proposed is dynamic spectrum sharing. And the dynamic feature talks about, we have all these different wireless systems. We have commercial, like 5G networks. We have scientific, like radio astronomy, and also federal, like public safety users. And all these wireless systems will come together, share the spectrum with temporal and spatial flexibility. So this sounds awesome, like good vision. However, the greatest challenge or barrier here is this like mutual trust issue, and that is, so everyone, whenever we bring out dynamic spectrum sharing, we're like, yeah, it's good, but we don't know. What if this happens? What if that happens? So how can we deal with this? So to handle this question, like the research I've been doing during my PhD is something called trustworthy dynamic spectrum sharing. So that is to bring mutual trust. And we have identified two major problems. So the first one is, say we have users of different priorities, have a higher priority to access the spectrum versus lower tier. And the problem is that we sometimes have interference from secondary users, so users with lower priority, who could cause interference that is more severe than the predicted values. And that means, the users with higher priority cannot really collect their samples because those are just corrupted with other interference. So what can we do with it? So the solution we are coming up with is something we need is better channel models, and we would like to driven this better modeling with machine learning. And the second major problem is that, what if this case happens? This worst case, when interference occurs, there is so far no way to recover or to handle it. And one example is just to simply turn off the interfere. And to handle that problem, the solution that we are proposing is that we need some automatic closed loop system to address these what if or worst case scenarios. And I would like to just quickly go through it, and given the time constraints, I don't really have time to dig into the details, but I would like to just give you like the high-level intuition of what this is about. So the first one is through learning approach. So we have proposed an explainable channel model via Bayesian machine learning, and what it means is that we have this channel estimation via this spatial loss field model, and once we have that data-driven spatial loss field model, what we can do is we can improve the shadowing prediction. So shadowing means the channel loss due to obstructions or like buildings or furnitures indoor. And to connect this research to error testbed, what we can do is that now we're considering a very different type of environment, and that is rural area setting. And this is like the simple map of the testbed here. And what kind of blew my mind is that I realized this is an area with a diameter over 60 kilometers. And the data sets I have worked with throughout my whole PhD, the largest area is like 16 kilometers squared. That's like the biggest difference here. And also, since we have talked about, there are like state-of-the-art weather sensors. So how can we incorporate those factors to have these time-varying, more adaptive channel models with those changes as well? And the second one is like, we have talked about automatic closed-loop systems, and the two systems that we have come up with, the first one is that we have this photoplex monitoring system for software radio platforms. And this system has been deployed in the real world for another testbed. And the second one is that we have this closed loop control for spectrum reuse between active users, so transmitters, and then passive users, which is in receive mode only. And to connect that with the error testbed, we would like to also monitor, these SDR platforms in the error testbed, and also probably for some other passive-active coordination as well. So to summarize with just 2 sentences, so to explore this new potential, trustworthy dynamic spectrum sharing, we still have a long way to go, but through error testbed, which enables us to validate experimentally and further improve this learning and systems approach, I would say the end goal is not really far away from us. So thank you.
Thank you, Jia. Our next speaker will be Abdul Eidiger from Florida Institute of Technology.
Hello, good afternoon. I know we run out of time, so I'll try to keep it shorter, and hopefully I'll get some question or feedback afterwards. So this is lightning talk, not a finished product or anything, just the preliminary ideas and work that we are currently trying to complete. And I guess the title is a bit unclear. It should be saying post-quantum cryptographic considerations for ORAN, so it's not necessarily the quantum computing, but the security part of the ORAN that I'm interested in. And before I jump into the presentation, as throughout the history, security always comes to last. For also this event, it happened to be the last presentation, the one related to the cybersecurity that we are doing. So in the ORAN, we have a couple of interfaces that if you are familiar with, you would know between the RU or the control unit or the system unit. So we have such interfaces between the components of the ORAN. And we have already some suggested encryption algorithms that ORAN Alliance provided for us. First of all, not many people even know this is the way it should be, and I don't know if even in ERA or in Dr. Peterson's tool they actually apply this or not. I mean, this is the way it's supposed to be, and again, I don't know if it's there. So whoever implementing this code, we need to talk and understand if it's actually there. But this is the way it's supposed to be until right now. And I'll show you this graph with the idea of telling how the computing power progresses is exponential. And obviously the future we don't know, but we estimate quantum computers gonna take over, meaning we're gonna have exponential increase in terms of computation power. And if you know how encryption algorithm works, you would understand the relation between. So we have encryption algorithms basically based on the fact that you don't have enough time to break it. So it's secure as long as no one is able to break it. Once you break it, it's no more secure. And we rely on the higher number of key size. So with the RSA, let's say, you cannot break it because you don't have enough resources. But if you have quantum computers, we might be able to. And it's coming along, right? So we want to make sure we are ready for it. That's why NIST already, just recently, I think 2 weeks ago or something, has approved some algorithms for post-quantum cryptography, meaning you can rely on this even for the sake of quantum computers become more mainstream. But obviously that is for more generic usage for ORAN or for 5G, 6G. Not many people even aware of such algorithms exist. I doubt even here in this room we have many people do know about it. So just to show you the interfaces, again, I was mentioning in the first slides, A1, O1, O2, E2, etc. So all of them already have some, again, by the ORAN Alliance, some encryption algorithms suggested. But what if we try to move it to the post-quantum era? So instead of TLS, if we can do it PQ TLS, that is post-quantum TLS. Or similar for IPsec, if we can change the encryption algorithms behind it. So this will be my last slide, and I'm running out of time. So if we can move all of them to the post-quantum algorithms, will ORAN still work as the way it should be? Because it has some time-critical applications that you need to obey the time limits, etc. So can we do this or not? And I'm mentioning ORAN, and I know not many people here interested in cybersecurity, but I need to be able to test this, and I believe ARA is one of the best tools that I can go with to run this new encryption algorithms in their test bed and see either yes, we can do that, or no, we cannot do that. So we need to, make another algorithms for specifically on ORAN or mobile networks. And that will be all. I hope I'll get some feedback later on, but we don't have time to discuss now. And thanks again.
Thank you. Thank you, Abdullah. So our last presentation will be done by Professor Jianping Pan from University of Victoria, Canada. And so he will present via WebEx.
I cannot share my slide right now. I need permission from the host. Can you see my screen now?
Works now.
Okay, great. So again, my name is Jianping Pan. I'm from University of Victoria in Canada. So here we are, on this island. So I think many people have already mentioned how important this agriculture and technology is. Again, we're dealing with something called a uneven supply and demand distribution problem, both in time and space. And there are additional challenges to the precision farming as well. As we have learned from other technologies, manufacturing, transportation, and commercialization, we want to ask how information and computing technology can help improve the agriculture nowadays. So what we propose is something called a space, air, ground integrated network approach to agriculture technology. And as already seen, we need to do sensing on the ground and above to bring the data to the cyber physics systems. And then we need to do the actuation near the ground, essentially we're looking at both high throughput and also low latency. So one promise is if we can collect more data, especially continuous data collection. So right now, most of the data collection is discrete and very coarse-grained. But if we have a continuous and also high fine-grained, data collection, a lot of new things can be incorporated, for example, data mining, machine learning, and also artificial intelligence with the large language model as well. So the approach here, we have when we look up, in the space, traditionally we use the geostationary satellite, but they're pretty far away, and also there's a high latency as well. So that's why the industry is moving toward the LEO. We have seen people mention about OneWeb, and also Starlink as well. And for the low latitude platform, we have the UAV unmanned vehicle, and on the ground, of course, we have both public and also private 3G, 4G, 5G, even 6G network in the future as well. So the question here is how we combine all these network facilities to approach the agricultural problems. So for example, we believe that if there's more competitors other than Starlink, there'll be a better market for everyone, which make it more accessible, but also affordable for the farmers as well. So for example, in the space broadband scenario, we have Starlink, OneWeb, they are operational already, and they are also Project Kuiper and the Lightspeed from Telesat, they are coming. Of course, there's other projects on the world as well. And for the direct-to-cell phone, let's say, kind of market, the SD Space Mobile, of course, like SpaceX, Starlink, they have collaboration with T-Mobile to provide a direct-to-cell service, promised to by the end of the year. But in addition to that, like kind of there's Space Mobile, like Link and Global Star, even Tentong, like kind of to provide certain services to the regular phone. And also, there one important thing, like I should mention, like there's something called Space IoT, which is the most relevant to the agriculture technology, because we needed those like low cost and low power consumption devices which can be embedded in different kind of equipment on the farm, and they can talk to the kind of let's say kind of device either in another side of the world or maybe like kind of over the sky. So for example, like a Swarm was like an independent company. They have been acquired by SpaceX, and in addition, there's many like CubeSat even built by university students nowadays. They were launched like through the rideshare program by NASA as well. So again, like there's a more possibility than what we think before. So here, like enough, I have just like a short video from the John Deere. Like they look at kind of how to use the drone to scan the field for like control, and also like do the crop spraying as well. And at the beginning of this like year, starting announced that they collaborate with like a John Deere to let's say equip the new and existing machines in US and also in Britain to kind of keep farmers connected for high precision like agriculture technology. So in this case, you can see like there's actually things happening, and for the research community, we want to understand this network even better to see like what's the real challenge behind this like technology and what's the future of this technology as well. So this brings to like kind of my last slide, also like some research work we have been doing in the space, air, and the ground integrated network toward like kind of the agriculture technology as well. So we are building a test bed in Canada, and also like we want to extend it to the US and around the world as well. We want to like see, let's say, for example, in this case, how the obstruction, because we know like there's a machinery, let's say, kind of around these like devices for let's say wireless communication, and how these like a metal shield could affect the kind of performance of like communication. So in this case, we have 3 dishes sitting side by side, Starlink dishes, and the two, one is like active, and the second one is like inactive, but we can still measure the kind of satellite link. And the last one is obstructed in the sense like we have some, let's say, kind of metal here to obstruct the view. So in this case, like we can see, let's say, what's the throughput performance and the latency performance impact of such like kind of obstruction, which is quite common on the like farmer field as well. And we also had some measurement, let's say, kind of for Starlink and OneWeb. In this case, like from Alaska to let's say Seattle, you can see like kind of in this case, like this particular kind of line is the fiber optic performance on the ground from Alaska to Seattle. It's quite stable. But of course, like kind of in some cases, Starlink can even achieve lower, let's say, kind of latency than the fiber optic because the shorter distance. And this particular one is the OneWeb, because OneWeb has higher latitude. There's like less satellites available right now, and there's less kind of limited ground infrastructure. So that's why overall the latency is higher than the kind of Starlink. But Starlink, because it's a unique like consumer-centered design, it has this like a 15-second handover behavior. So you can see like every 15 seconds, Starlink like jump to another beam. So this could cause like the delay jump to very high, even in this case higher than the second OneWeb, and also some like the handover loss happens as well. So that's why kind of, although there's mature technology coming up in the space, in the air, and on the ground, but we still have a lot of questions to answer about how to integrate them and how to like kind of put them to the use in the real world. So that's why kind of I like to invite everyone to join this like a test bed. So we have like kind of a coast-to-coast test bed in Canada, and we also like hope to let's say kind of extend it to the kind of nodes in the US as well. So for example, like Starlink added 6 new POPs in US like this year. So we try to kind of associate at least one dish in these POPs to be measured and also to be studied as well. And I think that's all my like slides prepared here.
Yeah, thank you, Jianping.
Okay.